All right, so the last part of chapter 1 is looking at intermolecular forces and solubility. I'm assuming most of you guys have seen intermolecular forces in your Gen Chem classes, maybe even a couple of times at this point, but we'll briefly go over them. Does anybody remember what the weakest intermolecular force is between two molecules? London dispersion. There's a handful of different terms, so I'll throw them all out. The first one's London dispersion. Some people will call this van der Waals forces. Some people will call this fleeting dipole. They're all the same term. People will use them interchangeably, and you may notice that I will refer to something as a van der Waals interaction or a London dispersion interaction. They're both the same concept. The main concept behind all of these is that electrons can't be everywhere at once. So let's take a look at a really simple case. Let's take the case of helium. Helium, if we look at it, it's atomic number 2. So what orbital does it have around it?
Just a 1s.
A 1s orbital. So we know that 1s orbital will be a sphere. Okay, and let's say we've got some electrons floating around in space, and I've got one electron right here, and if we take a snapshot picture of it, the other electron could be right there. So imagine just taking a camera, taking a picture of that helium atom at one moment in time. These two electrons, there's some probability that they'll be on the same side of that helium atom, right? So if we look at the right side of this helium atom, we could say, hey, this is a little bit electron rich, right? Both electrons are located on one side versus the left-hand side, this is a little bit electron poor. This is what's referred to as an instantaneous dipole. If we average it out, the dipole doesn't really exist, but if we look at a snapshot in time, there is a small dipole that could occur, right? So if we look at this, we could have another helium atom over here. Let me draw this a little bit bigger. And this helium atom could have an electron here and an electron here. So same sort of thing. We could say on the right-hand side of this helium, there's higher electron density, and on the left-hand side, there's lower electron density. This attraction occurs between that electron-poor side of one atom or molecule and the electron-rich side of an atom or molecule. So this is simply referred to as a van der Waals force or a London dispersion force. This is a stabilizing interaction. One thing that kind of bugs me in lower level chemistry courses is we tell students this is really weak. Weak is relative, right? So this is directly related to the surface area that's allowed to interact, right? So it's important to remember that molecules that have large surface areas interact more strongly than molecules that have a small surface area. So let's make a note of that. Specifically, a larger surface area to volume ratio will have a greater London dispersion attraction. Whoop. Another way of thinking of this is a larger surface area will have a higher or lower boiling point? Yeah, typically a higher boiling point. like I said, people think of this as a weak interaction, but I've got a cool example of how this is really a pretty strong interaction when it's applied on a large enough scale. So if you've ever seen a gecko can climb up a wall. If you feel their feet, they don't feel sticky, but they're still able to climb up a wall. This really comes down to what's on their feet, right? So if you look at a gecko foot under an electron microscope, you'll actually see this intricate webbed matting, right? That webbed matting has a huge surface area to volume ratio, and that allows them to have a London dispersion interaction with them and the wall so that they can actually climb up. There are actually a few tech startup companies that are trying to make gloves that do the same thing. So they're putting on high-tech material onto these gloves, and they're really, really sticky. So the thought is eventually we'll get to the point where we could Spider-Man up a wall, and that would be pretty neat. So let's take a look at some examples. Oop. All right, the first example I have for you guys is C5H12. So C5H12, we've got 5 carbons, 12 hydrogens. There's a couple different ways we can draw this out. One way is just a straight chain of carbons. So 4, 5, and we'll fill in our hydrogens. The other way we could draw it is with 3 hydrogens in a row, and then we'll have a branching pattern coming off of the end. So we'll have a CH3 group here, we'll have a CH3 group here, we'll have a hydrogen, hydrogen, and then we'll end with the CH3 group. So that's another way. We still have C5H12. The last one look a little bit like a cross. So we'll have CH3s all coming off of a central carbon. Which one of these do you think will have the greatest London dispersion force? The one on the left or the one on the right? The one on the left, right? If we think about the one on the right, it's actually a pretty compact molecule. We're forcing it into a sphere shape as opposed to a linear shape overall. So if we look at this one, we would say that this has a boiling point that is larger. And in fact, this boiling point is about 36 degrees Celsius. This one's 28 degrees Celsius. And this one's 10 degrees Celsius. So typically, the more branching that we have on a molecule, the less surface interactions we can have, and we drop the boiling point. An inverse way of thinking about that is the more linear a molecule is, the less branching it has, the more surface interactions it can have with a neighboring molecule. So that's an important thing to remember, is London dispersion forces can be pretty strong. They aren't necessarily weak. It really depends on the surface area of the molecules interacting. All right, there's another type of interaction that's a little bit stronger than London dispersion. What's that called? Dipole-Dipole. So this is an attraction between a delta positive, meaning a side of a molecule that's deficient in electrons, of one molecule with a electron-rich region on another. It's important to remember that in this case, this is not instantaneous. These are permanent dipoles. So just like on our problem of the day where we were looking at net dipoles, those were an example of a permanent dipole in a molecule. So for example, on that central one, that permanent dipole is pointing straight up and down. That fluorine side is very, very electron rich. That could be attracted to another molecule that has an electron poor region. So let's take an example of this. Let's say we've got fluoromethane. Let's determine where the net dipole is pointing for fluoromethane.
Towards it.
Yeah, straight to the right. Fluorine's the most electronegative element on the periodic table. So we can say, all right, this fluorine is going to be really electron rich. This side of the molecule, on the other hand, is going to be really electron poor. That fluorine's stealing or borrowing most of that electron density. If we have another equivalent of fluoromethane, the same thing, we've got an electron-rich region towards that fluorine, and we've got an electron-poor region over here.
I drew two fluorines.
Nope, thank you. There should be a hydrogen right here. Okay. And this results in a dipole-dipole attraction. There we go. So it's a stronger attraction because it's a permanent dipole than in the case of London dispersion forces. There's an even stronger type of dipole-dipole interaction. Does anybody remember what that is?
Hydrogen.
Hydrogen bonding. Hopefully this has been drilled into you guys by your biology instructors and your chemistry instructors. Oh, just one second. So with hydrogen bonding, I was talking about it with somebody the other day. Hydrogen bonding is really just a unique type of dipole-dipole, and it's a type that's usually defined as dipole-dipole interaction where hydrogen is bonded to either fluorine, oxygen, or nitrogen. So let's describe that. It's a special type of dipole-dipole. And it must have a couple of things occurring. Come on. Microsoft updated OneNote on me, and it does not like me anymore for some reason. Bear with me. What's the first thing we need for a hydrogen bond to occur? Hydrogen. Fair enough. We must have a hydrogen. That's a really important thing to remember. You don't have hydrogen bonding occurring when you don't have hydrogen. Number two, that hydrogen must be attached to which atoms again?
Oxygen, fluorine, nitrogen.
The way I always teach this in Chem 110 is hydrogen must be on the phone. So fluorine, oxygen, or nitrogen. It's an easy way to remember that if you don't have a hydrogen bound to your oxygen, nitrogen, or fluorine, you won't have any H bonding. The other last thing that we need is that there must be a lone pair to act as an acceptor, right? So you have to have a lone pair in order to have a hydrogen bond. So let's take an example of this. The most classic example of hydrogen bonding is water. So if we look at water, I'll draw a couple water molecules out here. We know that in this case there's some individual dipoles pointing towards oxygen. So I'll just draw some vector arrows there. Which means that the top of this oxygen is going to be pretty electron rich, right? It's stealing that electron density away from those hydrogens. However, this hydrogen over here is pretty electron poor because it's getting its electron density pulled away. So what's going to happen is this lone pair over here is going to be really, really attracted to this hydrogen. And this is going to be a very strong hydrogen bonding interaction. So we can see the hydrogen that's being donated is on the phone, and it's being bonded to a lone pair. These bonds can be incredibly strong. There are even some cases where they are stronger than covalent bonds, which is a little strange to think about. So hydrogen bonds play a critical role in the stability of biomolecules. So if you've studied amino acids and proteins, you probably remember talking about beta sheets and alpha helices, right? That's all due to hydrogen bonding. If you think about the spin in your DNA helix, also due to hydrogen bonding, a lot of hydrogen bonding is important in biology, so chances are you guys have seen it in your bio classes. The other cool example that I like to bring up with people is there's a type of spectroscopy in organic chemistry called X-ray crystallography, right? So you take a solid crystal sample and you actually shine X-rays through it, and you can determine the three-dimensional layout of atoms in that sample. If you do this with water, you actually can't tell where the hydrogens belong, right? So there's actually a three-dimensional network of hydrogen bonding. If we look at this hydrogen right here, it technically belongs to both oxygens now. It's kind of shared equally between both oxygens, and so it becomes really cool to see hydrogen bonding in X-ray crystallography because oftentimes you can't tell where the hydrogen truly is. All right, so let's go on a little bit. And let's compare the strengths of these. And I'll call these IMFs for intermolecular forces. Like I said, we've got London dispersion, also known as van der Waals or fleeting dipole-dipole. And then in the minute, we've got dipole-dipole. And then we've got H bonding over here. And we said that typically London dispersion is thought of as weaker. However, it's hugely dependent on surface area, and H bonding is typically thought of as stronger. Another way of viewing this is molecules that can hydrogen bond typically have fairly high boiling points. And these are typically lower boiling points. Like I said, London dispersion forces sometimes trump hydrogen bonding. It really depends on how much surface area you're dealing with. So that throws people oftentimes. So if you think about boiling water, water has a boiling point of 100 degrees. If you think about boiling oil tar, probably has a boiling point of over 100 degrees, even though there's no H bonding in there. So this is a good rough guideline. It's not absolute. Sometimes there are shades of gray. In fact, if we look at water, 25% of the attractive force between water molecules isn't even due to H bonding, it's due to London dispersion forces. Is due to London dispersion forces. So it's important to remember that this is just a rough guideline, it's not an absolute guideline. So what we're going to do is we're going to take a look at some molecules. I'll give you two molecules, and I want you to list what type of intermolecular force would occur within a container of each molecule. And then I want you to predict which molecule would have the higher boiling point. So let's take a look at a couple of them. So let's say I've got a box over here, and in this box I've got a bunch of CF4. And then over here I've got a box that contains CCl4. Let's take a look at CF4 first. What intermolecular force would occur between two CF4 molecules?
Dipole, dipole, and van der Waals.
Let's take a look at it. Let's draw it out. So we've got CF4. Is that going to be tetrahedral, trigonal planar, trigonal bipyramidal, bent? What shape will it be? Tetrahedral. So we'll have a fluorine sticking up. We'll have a fluorine over here. We'll have one kind of coming out of the page. And we'll have another fluorine going back. Is there a net dipole here? No, because everything's kind of pulling in equal and opposite directions on that central carbon atom. So this can't be a dipole-dipole interaction, and it's most certainly not going to be hydrogen bonding. That leaves us with London dispersion forces. All right, what about CCl4? Will that be London dispersion, dipole-dipole, or hydrogen bonding? London dispersion, same thing, right? Chlorine's going to pull equal and opposite directions around that central carbon. So we'll write London dispersion. Now the tricky question is, which one will have a higher boiling point if they're both London dispersion?
Chlorine is fluorine.
CCl4, why?
Large.
Surface area, right? A lot of people get really tempted to say mass. Yeah, mass is important, but the reality is that electron cloud around each one of those chlorines is huge compared to fluorine, right? Fluorine's really tiny. It's an atomic number of 9 and it's electronegative, as opposed to chlorine, which is atomic number 17. Chlorine has a giant electron cloud, and we can observe this when we actually measure the boiling point. In fact, CCl4 has a boiling point of 77 degrees Celsius. This is due to the large surface area on each chlorine atom. If we try to get the boiling point of CF4, it's actually a little tricky because it will boil at negative 128 degrees Celsius. So you have to pretty much try to freeze it or else it will boil on you. So just changing the halogens on there changes the boiling point dramatically. All right, now let's do another one. And this time I want you guys to try to work on it. I'm going to draw it out for you before I let you loose on it, though. This one's going to be a little bit more complicated. We'll do this compound versus, let's do this one. We have to determine the main intermolecular force that would occur if we had a container of each, and then try to predict which container would have the higher boiling point. Raise your hand if you think you got it. A few people? All right, does anybody want to help me out with the one on the left? You can throw up a hand. What do you think? One on the left, what's the main intermolecular force?
I'd say it's London dispersion forces.
London dispersion? Okay. Does anybody have a different idea?
Would it be dipole-dipole?
Dipole-dipole? This is tricky, right? So now we have to start thinking about geometries, right? If we look at that oxygen, we know oxygen's pretty electronegative. It's going to be pulling electron density away from this carbon and from that carbon. And we know that it's going to be about 109.5 degrees away from one another because that oxygen's sp3 hybridized. So where's the net dipole going to be pointing? Down, yeah. So you do have to account for that overall net dipole. In this case, it's going to be pointed down. If we look at the one on the right, it's actually the same sort of situation where we do have individual dipoles that are adding and they're pointing down. So they do have net dipoles. Do they have hydrogen bonding? No, we don't have a hydrogen directly coming off of that oxygen, so it's not hydrogen bonding. Okay, so now we know that these are both dipole-dipole. The next question I have is which one will have the higher boiling point? I heard somebody say the first one.
Yeah.
Was that Anthony? Why do you think the first one does?
Because it has those extra CH3 groups, more surface area.
Exactly. So those additional CH3 groups that are hanging off right here and right here provide additional surface area, which makes this molecule even stickier. So not only is there dipole-dipole, but there's additional surface area for London dispersion forces. So in this case, if we measure the boiling point, it's 68.5. I'm not going to quiz you guys on the boiling points exactly, but I will want you to rank which one's higher or lower. And this one's 35. So you can see that additional methyl group on each side adds a fairly sizable increase in boiling point.
Wouldn't it not be the best dipole-dipole because it might be, the oxygen might be electronegative, but the carbon isn't this two central carbons that are being pulled from aren't what's going to be on the outside. You'd have like a CH3 and an CH3. It's even less of an actual pull from them because it's so far away.
Yeah, in this case, you're correct in saying there's not going to be a huge dipole-dipole. However, if we're comparing apples to apples in this case, the molecule on the left and the molecule on the right, they have pretty much the same dipole-dipole. So then the question becomes which one has a greater surface area. So you're correct. Diethyl ether doesn't have a huge dipole-dipole interaction. Boiling at 35 degrees is a pretty low boiling point. That's a little bit above room temperature. All right, let's do one more. Nope, I already had all my. That's actually, I'll just be consistent. There we go. So we've got two isomers, right? Remember, isomers are molecules that have the same molecular formula but a different spatial arrangement. In each case, we've got C2H6O. Now the question is, what intermolecular force would each of them have if we had a container of each? Raise your hand if you think you got this one. All right, so it looks like people are doing pretty well on this. If we look at the one on the left, what would be the primary intermolecular force? Does anybody in the back have a educated guess? Hydrogen bonding, exactly. If we look at this molecule over here, we've got this hydrogen that's on the phone, so to speak, right? So this is a good example of hydrogen bonding. And we just said previously that the one on the right is going to be what? Dipole-dipole. I've drawn it as linear. We know it's not linear. That central oxygen's tetrahedral. So you can draw it linear. It doesn't do a great job of showing the net dipole. But we know that from our previous drawing, it's going to be dipole-dipole. Which one will have the higher boiling point, the left or the right? Left, exactly. So this will be a higher boiling point. And this one will be a lower boiling point. Significantly, in fact. I think ethanol, I'm trying to remember its exact boiling point. It's in the 60s, and dimethyl ether is actually a gas. So very, very different boiling points. Does that make sense? Mostly review? Yep.
How exactly would that dipole-dipole reaction happen on the right since the central atom would be involved?
Yeah, so let's actually draw that out. I'm going to erase this really quick. And I'm going to draw this slightly differently. So we can see the three-dimensionality of this, right? Oop, I need a black marker. So we know we've got lone pairs that are kind of sticking out in this direction. We know that there's going to be an electron-rich region on that side, an electron-poor region on that side, right, kind of behind that oxygen. If we've got another equivalent of this molecule, it'll essentially stack with itself. So that we've got an electron-rich region over here, an electron-poor region over here, and now these two sticky ends will be attracted to one another. That's going to be the dipole-dipole interaction. So you can kind of think of these as stacking triangles. Good question. Yep?
How much does the steric number of the electronegative atom on the left affect the net dipole? Because the way it's shown right there, it's showing like it's pointing from the carbon to the oxygen, the hydrogen to the oxygen. So those two vectors, if you add them, the magnitude of the overall vector would be...
Oh, that's a good point. So you do have to think of it as true vectors. So you'll have a dipole. Let's actually draw this a little bit differently. So the question was, how does the positioning of the atoms affect the overall dipole? Let me fix this. If you think about this vector over here, this is going to be much, much bigger than this vector. That's going to be a smaller arrow. That does matter to a certain extent, but I wouldn't be overly concerned about it. Just try to remember, if there's a net dipole, you're going to have a dipole-dipole interaction. And if you've got a hydrogen coming off of fluorine, oxygen, nitrogen, that's going to be an even stronger type of dipole-dipole because that vector is going to be huge.
Well, what I was kind of thinking about was if the carbon were double bonded to the oxygen, so you would have the different geometry.
So your question is, what if we had a double bond there? If we had that, we would have to get rid of one of these lone pairs, and that oxygen would be positive. That changes the electronegativity of everything.
So, but the net dipole, is there a big difference between that and what we had before? A big enough difference for us to care about?
Not a big enough difference for you to really care about in this case. You still are overall looking at a net dipole. If a net dipole exists, it's going to be dipole-dipole. Yeah. All right, so let's move on a little bit. The last section of Chapter 1 talks about solubility of organic molecules. This is a pretty easy concept. And this is a concept that I just call like dissolves like. What does that mean? Well, it means if you've got a compound with a certain intermolecular force, chances are it will dissolve another compound with a similar intermolecular force. A good way of thinking about this is oil, which is typically a molecular formula of CXHY, and water. We all know that these won't mix, right? Because if we think about oil, if it's a hydrocarbon, it's going to have London dispersion forces. And water does H bonding, which means that these won't mix well. That's the general broad definition of how organic molecules dissolve. The more similar their intermolecular forces are, the most likely, or more likely they will be soluble. For ionic molecules, things change a little bit. What does it mean when something's ionic?
To be a metal and a non-metal, or to have over 1.7 electronegativity difference.
Yeah, so yesterday we said if you've got a really big electronegativity difference, there's a transfer of electrons, you're no longer sharing. So you'll have one side that's positive, one side that's negative, that's ionic, right? So it's completely separate positive and negative side of an ion. For ionic molecules, they tend to dissolve better in hydrogen bonding solvents. How many of you guys remember your solubility tables from Gen Chem? This isn't an across-the-board rule. There are some ions that will dissolve really well in water, which H-bonds, and there are some that will just sit there and stare at you, right? So this is a general trend, is ionic molecules tend to dissolve better, but it's not an across-the-board truth. And the way they typically dissolve is you'll have a bunch of water molecules, for example, that will surround a cation. Why did I have the oxygens pointed in and not the hydrogens? Yeah, because we know that these oxygens have delta negatives. These delta negatives like to snuggle up against that cation. Inversely, if we've got an anion, we would have a bunch of hydrogens pointed towards them. Because these hydrogens are deficient in electron density. So we'll have a delta positive close to each of these hydrogens. That'll be really attracted to an anion. Like I said, this isn't an across-the-board truth. So I've got a weird example for you. Let's say you're a chemist and you do need to dissolve an organic molecule that has London dispersion forces in water. What do you do?
Break the phospholipid.
You could heat it up if you really try to, but let's imagine trying to mix oil and water. You could heat it up all you want and it's still going to separate out into layers. An emulsifier, right? So most of you guys have worked with emulsifiers. They're also known as what? Soap. So soap is a weird example of forcing something to go into solution, right? Soap is referred to as an amphiphile. Meaning it will dissolve both things that have London dispersion forces and things that can hydrogen bond. So if we draw out a soap fatty acid residue, essentially we have a long carbon chain coming off of one end. And then over here, we've got an oxygen with a negative charge. If we look at this end of the molecule, this will dissolve nonpolar molecules. We know nonpolar molecules have London dispersion forces. This looks like a long hydrocarbon, so it will also have a lot of London dispersion forces. And then this end, whoop, I put a positive there, sorry. Which should be lone pairs. And then this end of the molecule will dissolve polar molecules. So what we'll do in a lot of our lab settings this year, or I guess I shouldn't say a lot, in a couple of our labs, I'll ask you to add a reagent that acts as an emulsifier. It's similar to soap in that it will take one portion of your mixture, pull it into solution along with another portion of your mixture that has vastly different intermolecular forces. And it's a wonderful tool. Oftentimes chemists are trying to use this more and more because water is the best solvent we can use. It's cheap, you can heat it up, it's easy to recycle, you can ship it vast distances. If you have a spill of water, oh no, you've watered some grass. So water is the new universal solvent. Emulsifiers are becoming really common, and they're a good tool of mixing organic molecules with a bulk solvent like water.
I just spell emulsify.
Oh man, you're going to check my spelling. Emulsifier, I think. That's, yeah, phonetically, I'm going with that. All right, I think that's where we're going to end off today. Next week, remember, we've got our quiz first thing when we get in here. Then we'll start into Chapter 2. So if you do want to read a little bit ahead in Chapter 2, you're more than welcome to.